Hello children, how are you all? So how was the first part of the chapter 3, atoms, molecules? Have you enjoyed it? Yes, that's good of you. Right now, we'll now get into greater detail of that part. We have seen that the ancient idea about the matter's nature. So it was told that the matter is made up of very small particles called as atoms by some of the ancient philosophers, but there was no ground proof for that. That is, I should say, there was no practical proof for it, for the existence of particles called atoms. They were just taken like that. Okay, right. It was only a thought. Now, after that, the modern scientists they had an idea about the elements and compounds. One scientist by name Antoine Lavoisier, he conducted experiments and he called them as the laws of chemical combination, right? And he gave an idea how elements are combining. So elements are combining. So our substances are combining. Whenever substances are combining, and he found that there was no loss or gain of mass. The mass before the chemical reaction and after the chemical reaction, that remains same. Okay, so this he put forth as a law, and that we call it as a law of conservation of mass. That's it. The next one, scientists again after him and along with him, Joseph Bell Proust and a few other scientists, they have found that whenever elements are combining to form, or the elements are combining to form the compounds, in the compound the elements are maintaining a definite ratio by mass. Whatever the type of source or method of preparation of that particular compound be, we find that there is a definite ratio or proportion by a mass of those elements that are reacting, okay, are forming the compounds. So children, right, so scientists were now trying to explain these chemical laws of chemical combination, both law of conservation of mass and the second law, which we stated that the law of definite proportions. These were to be explained, and scientists were thinking how to explain these. Why is there no loss of mass during chemical reaction 1, and why are elements in a particular compound maintaining the same proportion always? So that is the thought, and that one scientist, one school teacher, a chemist, he got a clue into this and gave a very vital and the whole chemistry turning, I should say, idea about matter. And he was none other than John Dalton, a humble schoolmaster who has given some assumptions about the matter based on these two laws of chemical combination, and he put forth what are called as Dalton's theory of atom, or we call it as Dalton's atomic theory. Okay, children, right? We'll just see the postulates what John Dalton has told. Right. So children, we are here now studying atoms and molecules, and now we'll put forth what is called as Dalton's atomic theory, the postulates put forth by Dalton's atomic theory. What is this theory? The first postulate, all matter is made up of very small tiny particles called as atoms. So what do you mean by all matter? It's the elements, the compounds, the mixtures, whatever they be, they are all made up of atoms. Now the second postulate of Dalton's atomic theory, what is that? That is right, atoms, they are indivisible. Then next, they are indestructible, that you cannot destroy them. Indestructible, right? Good. The next, and what else, children? They are indestructible. The next, they cannot be created, so they cannot be created. They cannot be created. So you just cannot create atoms. They are so tiny, first, and they are very small particles, right? Good, they cannot be created or destroyed. During what? During chemical reactions. So during what? Chemical reactions. Right, okay, that's the thing. Now third, so what else? What else? Right, atoms of elements. Atoms of an element are alike. What do you mean by alike? They are alike means they are all same. They are all same and in all respects. What do you mean by all respects? So their masses, they are same in masses, and their chemical properties. Right, good. That's it. So fourth one, the fourth postulate: atoms of what? Atoms of different elements. Now, so this was about same element. Okay, they are alike. Different elements are different or unlike in all respects of their masses and chemical properties. Okay, right. So that's a fourth one. Fifth one. Now we know well that atoms combine. Where are these atoms? These are present in elements. Now atoms, whenever they combine in whole numbers, in ratios of whole numbers. So atoms combine in ratios of whole numbers. Whole numbers. Now what do I mean by these whole numbers? You know well, 1, 2, 3, 4, they are whole numbers. They are not 1.5 or 1.5, 1 3 by 4, 1 5 by 6. No, it's not like that. They are not parts. They are always combining in the form of whole numbers. That is, one atom combines with two atoms of some other element, and three atoms of one element combined with say 5 atoms, but never combine with 5 atoms combining with 2.5 atoms of other element, or 10 atoms combining with 12.5 atoms of other element. No, it's not like that. Always in whole numbers. Right, next, the fifth one we have seen, children. Now we'll see the sixth one. Now how are these combining? They are combining the atoms of the elements. Okay, they are combining in a definite ratio of masses. So the elements there, they are combining in definite ratio of masses. So, right, that's the thing, children. So what is that? Now atoms, when they combine in whole numbers, right? Atoms combine in definite ratios. Definite ratios. Okay, right. So they combine in actually whole numbers, right? Okay, they combine in definite ratios. Okay, these are separated. So we can just talk it as in whole numbers. I should say this is in whole numbers, right? Good. Atoms combine in whole numbers, right? Atoms combine in definite ratios. So every compound will have atoms or particles, compound atoms, in which atoms of the elements, they are combining in definite ratios. So children, so these are the 6 postulates of Dalton's atomic theory. Okay, right. Now, how do these explain how did these explain the laws of chemical combination? So atoms are indivisible, indestructible, and cannot be created. So this second part, the second postulate, it explains the law of law of conservation of mass. That explains law of conservation of mass. So that's the thing. So the second postulate is explaining the law of conservation of mass. Okay, right, good. The next one, you see children, now this thing, that is the sixth postulate is explaining about the law of definite proportions. He said, now why are elements combining and in definite ratios of masses? Is there any reason? Yes, there is a reason. Why? Because atoms of those elements, they are combining in definite ratios of numbers. Definite ratio of numbers. What numbers? What numbers? Right, okay, good. So they are combining in definite ratios of numbers. Okay, so that is the reason why the elements, they are combining in definite ratios of masses. So all the elements are having same atoms of same mass. That's what this particular second, the third postulate tells. So naturally, if atoms of the same elements are having the same masses and chemical properties, okay, that is it, same masses, if they are combining in definite ratios of numbers, if the atoms are combining in definite ratios of numbers to form what are called molecules, naturally the ratio of their masses, or ratio of the mass of the elements combining to form those elements would be constant. So children, that is what. Now the second postulate explains the indivisibility, indestructibility of atoms, which again explains the law of conservation of mass. As atoms cannot be destroyed or created, mass can neither be created nor destroyed during a chemical reaction. Now the second law of chemical combination, which is called as law of constant proportions, is explained by the sixth postulate, as the sixth postulate tells that atoms, they combine in definite ratios of numbers. So as they are numbers and the masses of the elements, okay, masses of the atoms masses of the atoms of the same element, they are same. So the number of atoms combining, as they are not changing, the masses of the atoms combining or the masses of the elements which are forming that compound, they always bear a simple ratio, that is a definite ratio. So this is about the explanation of the laws of chemical combination by our scientist Dalton. Okay, right, children, are there any flaws in this? Okay, right, at that time when Dalton proposed this, it was accepted somewhere in 1803-4, that time, 3. He proposed this law. Okay, right. And during this time, that was widely accepted, and people thought that atoms, yes, are made, the whole matter, all the matter is made up of a very tiny particles called as atoms, very good. And there is no further particle possible, and atoms are thought to be spherical, ball-like, and atoms are indestructible. Okay, right, and the atoms are not further divisible. Okay, that was accepted for a long time, and till the end, that is somewhere around 1800 and 80s, 90s. During that time, some of the scientists, they performed experiments on the passage of electricity, and you know the history, that is atoms were found to contain very fine particles which are called as subatomic particles. Later on, they were named as electrons, protons, and neutrons. So the divisibility of the atom, the indestructible property of the atom was gone, or otherwise you say that has to be discarded. Right, okay, good. Now anything else? Okay, that is what we'll be seeing, we'll be listing up. So atoms are indestructible, that is done away because of Thomson's findings. Right, atoms are destructible. Not destructible, sorry. Atoms are indivisible property, that is that has to be done away after the discovery of electrons by Thomson. And the subsequent scientists like Goldstein and also Chadwick of protons and neutrons respectively, and a few other particles. Later on, it told that atoms are divisible. Okay, that's it. Now next, now what about this? What about this idea? Atoms of same element are alike in all respects. Okay, good. But he said something here. They are also similar in nature, in mass. Is it right? So later on, some scientists they have found there are atoms, like I write children, 1H1, 1H2, 1H3. These atoms, these are the representations of the atoms. Very carefully check. Okay, they're all hydrogen atoms. They have the same atomic number, but when you carefully observe, the masses are different. So it is possible for atoms of the same element to have different masses. So that is done away with. Okay, so it's not a flaw actually, I should say. The subsequent scientists who were doing the researches, they were finding all this. Dalton was never wrong. I should say he is not wrong. To his level, he has done some good, some work. But later on, when the work was carried on, it was found there is a flaw in this statement that atoms of same element, they are all having same masses. That's not right. But they are not having. So almost all elements will have what are called as isotopes. These isotopes are atoms of same element having different masses. So children, that's not right. Later on, it was found that. The next one, we go to this. Atoms of different elements are different in all respects in their masses and chemical properties. Okay, chemical properties, they will be different, right? But their masses, there are elements. Now we'll talk about two elements. Say argon and calcium. So I write argon as 18, argon 40, and this is 20, calcium 40. Okay, right. So you see they are having different atomic numbers, and you see the mass numbers or the masses. So you will be surprised to see that the masses are same. So what do you see? So these atoms which are having different atomic numbers but having same masses, they are called as isobars. What are they called? Isobars. So isobars are not accepting this rule, or this what rule? Fourth postulate is not according to this, or otherwise the discovery of isobars later has proved that atoms of different elements need not have different masses. Okay, that's the thing. Now next, children, this is how Dalton's theory of atom was to some extent was able to explain the laws of chemical combination, but there were some flaws which were found by the subsequent scientists. Children, but the greatest stepping stone to chemistry or the understanding of the particle nature of the matter was proposed by John Dalton. So, do not forget his contribution to science. Today, all the material science, that is the chemical reactions in all, okay, that's based on what is called the atomic structure. Okay, later on, scientists took the cue from him and developed the structure of atom. Today, the study of the atom has resulted in so many new things, not only in the chemical reactions, but also in other fields. Okay, right, like your radiations, there are waves forming, your communication, it's all originating from the atoms. And for your information, atom can be destroyed also. Is it possible? Yes, there are divisions made in atoms by way of what is called as nuclear reactions. That's not complete destruction, but that can be divided. The atom can be divided into fragments, and that causes what is called explosion. That explosion and continuous what do you call a fission chain reactions, you get a lot of energy that we are at present tapping from what is called as nuclear reactors. So they are called the nuclear reactors. So it's all atoms children there. Okay, right. So atom is so important, and the one who gave an idea about these atoms is not an ordinary person, I should say. A humble school teacher later on gave these assumptions which were able to explain the laws of chemical combination. Not only that, that paved what is called as a stepping stone for the development of the structure of atom. And today we are standing, and I am bringing out this video, and that's carried through waves, through internet, and all communication. It's coming to you, reaching you. It's not an ordinary achievement. Let us salute his master, John Dalton. Thank you very much.